So first of all, thank you to Warren Fox, who suggested it would be helpful to have a little bit more content in seminar related to radiation safety, and for suggesting colleagues at TRIUMF who might be able to give such a presentation. It is our pleasure to welcome Anne Trudel. Anne's career has spanned many different areas at TRIUMF, Canada's National Laboratory for Particle and Nuclear Physics. She completed her PhD in subatomic physics in 1987 and carried out research in intermediate and high energy physics at TRIUMF, CERN, and DESY. Her work included building and commissioning different detectors used in subatomic physics research. In 1996, she joined the Radiation Protection Group as a health physicist, capitalizing on her expertise with detectors and applying it to the protection of health and safety in the workplace. Before she retired in 2020, and she promises me that she's only really semi-retired at this point, Anne headed up a team of 16 physicists, engineers, and technicians who constitute the Office of Environmental Health and Safety. The office is responsible for ensuring that TRIUMF operations are carried out in a manner that maintains industrial and radiation safety for all employees, and for ensuring the protection for members of the public and the environment. So we don't get to talk about radiation very often in this forum, and really looking forward to this presentation. So welcome, Anne, and please go ahead and unmute.
All right. Good afternoon. It's my pleasure to be here. And I have kept in mind that radiation is not likely everybody's background. So I will be hoping, I'm going to look to cover that in a primer. But before I get there, I do want to give credit to my predecessor in this position, Lutz Moritz, who did really a lot of the pioneering work in accelerator health physics over the years that he was at TRIUMF, and he headed up environment, health, and safety before I took over in 2006. As well, some of the work that I'm going to be presenting was done by a couple of our radiation physicists that are still at TRIUMF, Joe Mildenberger and Ricardo Augusto. Okay, I seem to have lost the ability to advance my slide. Hold on a minute.
You might just have to click in PowerPoint.
There we go. So as I mentioned, I'll cover a radiation physics primer. So I'm assuming essentially not even a high school level of physics. I apologize to those of you who have more of a background in physics than that, but maybe you'll appreciate a review. Then I'll speak about TRIUMF and in particular the regulatory environment for a nuclear facility, and then address the three main topics that I think are pertinent with protection, occupational and environmental health, personnel dose management, environmental risk, and a little bit on facility decommissioning. So what is radiation? We have electromagnetic radiation shown here, an electromagnetic spectrum. I'm just trying to move my PowerPoint. Sorry, there we go. Minimize the Zoom window. Yeah, so the picture shown here shows a spectrum of electromagnetic radiation going from, not sure that you can see my cursor. Let me just get that going too. Going from long wavelength, low frequency radio waves, progressing up through microwaves, infrared radiation, which refers to a component of the spectrum below the red visible portion of the spectrum, and then visible, ultraviolet, X-rays. X-rays are in fact generated from an atomic process. They're higher energy electromagnetic radiation, and gamma rays are generated from a nuclear process, and we'll see a little bit more of that. And then a component of cosmic rays, very high energy, is also electromagnetic radiation. And everything above ultraviolet up to cosmic is ionizing radiation. And we'll see why that's important in a minute. I wanted to also talk about radioactivity. So I have a cartoon of an atom here, and it's a cartoon because the electrons are shown as individual particles. It's a cartoon of a carbon atom. So we have 6 electrons, but really this electron is really a cloud. It's a probability distribution around the atom, but this showing them as particles makes it easy to talk about. And then the nucleus is shown quite large, so we could see it. But in fact, it's about 1,000,000 times smaller than this if the electrons were going to be that size. So we have a neutral carbon atom here. The nucleus consists of 6 protons in red and 6 neutrons. The protons are positively charged. The electrons are negatively charged. Hence, the carbon atom is neutral. And this is referred to as carbon-12 because there are 6 protons and 6 neutrons. We can also ask, well, what happens? Can we add a neutron? And we can, and then we form carbon-13 with 6 protons and 7 neutrons. And both of these nuclides are stable. They're both isotopes of carbon, and they are stable. In nature, carbon consists 98.9% of carbon-12, and a very small fraction is carbon-13. So we can then ask, well, what happens? Can we actually make a nucleus that has 6 protons and 5 neutrons? So I might not have made clear, but the reason these are isotopes of carbon, they all have 6 protons. So here with 6 protons and 5 neutrons, we have the isotope carbon-11. Now it turns out we can make carbon-11, and you'll see we make it in accelerator facilities, but it isn't stable. It actually decays, and it has a very short half-life, and we'll talk about half-life in a minute, and it decays. It's no longer carbon now. One of the protons has decayed to a neutron, emitting a positive electron called a positron. So it's become boron 11. Note that this is a change in the configuration of the nucleus. And we can also think about an isotope of carbon, carbon-14, where we've now got 8 neutrons, 6 protons and 8 neutrons. And for those of you who are familiar with carbon dating, you would know about carbon-14. It's this isotope, and it is also radioactive and emits, the neutron decays to a proton. Again, this is a nuclear process, and a beta particle is emitted. So both of these are radioactive isotopes of carbon. They no longer say carbon-11 and carbon-14 now because they're decayed to their stable progeny, boron-11 and nitrogen-14. The radiation that's emitted is ionizing radiation, as we'll see. These are actually 2 types of beta particles. And the fact that they decay is where radio is the source of the radioactivity. There's more information at this URL if you're interested. So we use the chart of the nuclides as a convenient way of capturing information about radionuclides. So you can see here, here's the 4 isotopes of carbon that we were just talking about. The chart of the nuclides plots number of protons on this axis. So it's 6 protons for all of the isotopes of carbon, and number of neutrons on this axis. And I'm only really showing you the bottom end of the chart of the nuclides. We have nuclides that go all the way up to uranium and even above that. And you'll see, I'll show you one of those a little bit later when we talk about what we do at TRIUMF with accelerators. The 2 important properties of radionuclides And one you can see here is captured by the color, it's called the half-life. And radionuclides, that is nuclides that are radioactive, have different half-lives. And the color here captures whether it's a very long half-life or as we had in carbon-14, and or to a very short half-life or even shorter in the millisecond or microsecond level. Half-life is the time it takes for a quantity of radioactivity of a radionuclide to decrease by half. So we measure radioactivity using a becquerel as a quantity of radioactivity, and it actually corresponds to 1 disintegration per second. We saw that for carbon-11, the half-life is 20 minutes. So if we start with a certain quantity of radioactivity at time 0, and then measure it again 20 minutes later, we'll have half of it. Another 20 minutes later, we'll have a quarter, and so on. So radioactivity, half-life is an important characteristic of the radionuclides. I didn't mention, but the ones in black, as we saw with carbon, are stable. So you can see just by looking at this chart of the nuclides that we have many more radioactive than we have stable nuclides. Or at least we know about them. We have created them at some point, or some of them are primordial, have existed since the formation of the Earth. Another important property of the radionuclide is the type of radiation that it emits. And I show here 3 common types of radioactivity. An alpha particle is a chunk of nuclear matter, so it's 2 protons and 2 neutrons. Betas are the positron and the electron that we saw. One is positively charged, one is negatively charged, so we could have beta plus, beta minus. And gamma rays we saw are a form of electromagnetic radiation. And this here shows how those different types of radioactivity that are emitted by radionuclides interact with matter. So, some alpha particles can be stopped with very little material, whereas betas are more penetrating and gammas are the most penetrating. And we use these properties of the radionuclides in providing protection for personnel in laboratory and also in diagnostic applications, such as a lead apron that's worn during a dental x-ray. So I mentioned ionizing radiation, and this type of radiation that we've just covered, whether it's the high end of electromagnetic radiation or alpha, betas, are ionizing radiation. That means that when that radiation interacts with matter, whether it's passing through a material or whether it's passing through tissue, have the potential to remove an atomic electron from the atom. And that's what we see here. That process can also break chemical bonds, example of say, a DNA molecule, and that can lead to the incidence of cancer. The process of ionization also deposits energy in the material, in the tissue, and we use that to detect radioactivity, to detect radiation. So there are 2 types of radiation that we talk about. There's the physical deposition of energy in the material, and that is called a gray, named after Louis Harold Gray, who's one of the pioneers in the field. A gray is a lot of radiation. Generally, we talk about a milligray and or a microgray. And again, there's the radiation passing through either matter, your detector, and or tissue, and there's energy that's deposited. In fact, the quantity gray is a joule per kilogram. And that's the physical dose. We need a unit for the risk associated with radiation, and that's the biological dose, a sievert. And again, the sievert is a large quantity, so we talk about millisieverts and microsieverts, as you'll see in a minute. And what that is the energy that is deposited in the body multiplied by a radiation factor and a biological factor. The radiation factor depends on how the radiation deposits energy in the body. And we saw a little bit of an example of that based on how the alpha particle, say, is absorbed in very little tissue versus a beta that has a greater range, and a gamma. And the other, the biological factor, depends on how the sensitivity of different organs to radiation exposure. So the important takeaway here is that the physically measurable quantity is the gray. The risk, the dose that captures the health risk is a sievert. So you won't hear me talk about grays, but you'll hear a lot about sieverts. Okay, so the last thing on sources of radiation before we move on to TRIUMF and regulating nuclear facilities is captured in this slide here. And what you have here on the left are in the diagram are the 4 different sources of, actually 5, of radiation exposure that comes from our everyday environment, or so we call it background radiation exposure. And you'll see when we go on to talk about dose limits that we're talking about occupational doses that's over and above this background radiation exposure. But the background radiation exposure is useful for providing a context for the dose limits. Oops, sorry. So we have the main sources of radiation exposure come from radon, inhaled radionuclides that come from the decay of uranium and thorium in the Earth's crust. There's 2 sources of radiation, or the 2 contributions to dose to an individual from the actual radionuclides in the Earth's crust, but that's only about 1/4 of a millisievert. And here you can see from radon itself, it's about a millisievert. As well, we get a little bit of a dose, another 1/4 of a millisievert, from radionuclides that are present in food that we consume, whether that's potassium in milk or other radionuclides in vegetables and Brazil nuts. And so generally, though, on average, the annual dose in Canada from background radiation is 1 to 3 millisieverts. In Vancouver, it tends to be a little bit lower because we have this onshore offshore breeze that essentially means we don't have very much radon. Also, we don't have the Canadian Shield that would give us higher levels of radon. But if we go to the interior, for instance, like Clearwater, the natural background radiation is about 6 times higher, and that comes largely because of radon. So then that's when essentially ensuring that you don't have radon collecting in your basements and in your house is important. I capture here as well, just to provide context, medical dose from a medical X-ray. It's a single X-ray would be about 20 to 50 microsieverts, and dose from a flight because you're at a higher level in the atmosphere, so you're exposed to higher levels of cosmic radiation, a few microsieverts. This would be a Vancouver-Toronto flight. All right, moving on to TRIUMF. Well, what is TRIUMF? It's Canada's Particle Accelerator Center. We do different types of physics, particle physics, looking at small, tiny particles, nuclear, where we probe the structure of the nucleus. We also do nuclear medicine and material science. At the heart of the lab is the 520 MeV main cyclotron, which is 45 plus years old now. But we also have other cyclotrons that we use for isotope production. These are lower energy. They are between 30 to 40 MeV. And we have a small 13 MeV cyclotron here, self-shielded, that we use for making isotopes for positron emission tomography. I think I have my poll here now with regard to accelerator applications.
All right, here it goes. We usually wait for 75 to 80% of people to respond.
Okay.
I realize now that I probably didn't set this up correctly, so people may only be able to select one answer.
Oh, I see. Okay. Okay. All right.
No, I think I got the select too, Sarah, just so you know.
Oh, you did? Okay. Catherine and I also set it up simultaneously, so I'm not really sure what version people are getting.
It looks like the 100% for medical isotopes is coming down as people are selecting some of the other ones. Okay.
Give folks a couple more seconds. There's just a little bit of reading and thinking that needs to happen here.
Right.
And I will end it on that and share the results so everybody can see them.
Okay. So do I do
stop sharing and you'll have to clear that from your screen?
Okay, great. All right. So yes, they're all in fact applications of, I have to click here again, I guess, to get my control back in, of commercial applications of accelerators. So I wanted to say a little bit about what a cyclotron is. It's the machine that uses an electric and magnetic field to provide acceleration of particles in a circular orbit. So the electric field happens in this gap here. We call it the D gap because each of these, the blue and the red, look like Ds. And that's where an electric kick of about 90 kilovolts is given to the ions. And the green lines show the magnetic field that keeps essentially the particles going around in a circle. So we alternate the voltage between the Ds to stay in step, essentially with the particles as they are accelerated from one half of their orbit to the next half. And as they get more and more energy, they circle in a ever growing radius. And that's how we get them to 520 MeV. I neglected to mention, but we get accelerated protons essentially to 3/4 the speed of light. That means traveling between Vancouver and Halifax in milliseconds. Now, that's how we accelerate particles. What we are accelerating are in fact negatively charged hydrogen atoms. So I call them protons because the nucleus of a hydrogen atom is a proton, but we've tacked on an extra electron to make it negatively charged. And the reason we do that is in fact so that we can easily extract the protons that are moving at a high speed. And that's captured in this next slide here that shows, or this next diagram that shows a stripping foil where the negatively charged hydrogen ion enters on the left and exits on the right. And most of it has the 2 electrons around the hydrogen atom have been stripped away. And the particle, because it's positively charged now, bends in the opposite direction in the magnetic field and comes, as opposed to keeping going around in a circle, comes to the outside of the machine. And the reason we do that, as opposed to just using positively charged protons, is that we can essentially choose the energy where we want to extract the beam by introducing the stripping foil either at a low energy, a smaller radius, or at a higher radius. Here's the inside of the cyclotron. Of course, we don't get to see the inside of it very often. It's a large vacuum tank, and everything has to be kept quite clean. It's a large machine, as you can see, 18 meters in diameter. Oops. And the accelerating are the RF accelerating electrodes are these cavities right here, and the D gap is right in here. You don't see the magnets. The magnets are 4,000-ton magnets that sit on the outside of this. This whole large tank is in a vacuum, so we also need a lot of mechanical forces to keep the tank from collapsing on itself, and that's all part of the accelerator. I mentioned already that we accelerate to 75% the speed of light. So we extract beam to some of these different facilities. The blue ones here, where we're using the proton beam itself, we have two targets with smaller beam lines that take mesons that are produced from the proton beam on the target. The orange beams, we collide with targets here and here. This is our new facility. And we extract the radioactive ions that are made. And I'll say a little bit more about that in a minute. So just to provide you context, I'll show you some photos. We'll see this photo here. We'll see a photo of the experimental hall here. What you'll note when we see the photo here is that there's a lot of shielding in place. You won't see these beam lines, but by the time we're up here looking at extracted radioactive ion beams, the radiation fields are much smaller, and so we're able to have people present where the beam is. Of course, the beam travels in a vacuum envelope the whole time. It's not in air, and I think that will be visible as well in some of our in some of the pictures. So here's the large pile of blocks. Note we have a 50-ton crane for manipulating these. The beam line itself is buried down, about 6 feet above the floor, which is way down here, and about 15 feet inside from the wall here. The shielding that's in place is largely concrete that we use, and it's about 3 or 4 meters thickness of shielding. In fact, we have 2 production targets, and you can see where those are because that's where the shielding profile is in fact higher than in other areas. So one other point is, although we're talking about radiation protection and the hazards with radiation, this is an accelerator lab. You can see that we have fall arrests that we need to use whenever there's access on these blocks. We have large power supplies to supply and steer all of the beams to get them from the accelerator to their target. So there are a lot of other conventional hazards associated with occupational health and safety at TRIUMF. This here shows a photo of, this is our Proton Eye Therapy facility. We had a run of about 20 years. I think in the last year we've decommissioned it, but this shows where the patient would be positioned, and the beam, very small quantities, of course, but well targeted to target the tumor at the back of the eye. And we have a couple of experimenters here. I've included them because I also wanted to point out the radiation dosimeter that all of our experimenters, all of our staff wear when they're working in the lab. This is a picture of the Isoac experimental hall. So now you don't see the shielding, but you can see the beam line down here, bringing essentially the radioactive ions. We do have radiation monitors, and I'll say a little bit more about those. And you can see the beacons from them right here. They're attached to the monitor itself is down at the beam height, and there's a cordon that comes up here. The radiation monitors do alarm in our control room as well. And I've got a photo here of a cyclotron operator. They would be alerted if radiation fields get above a certain level. All right, well, what do we do with our accelerators? So here's our chart of the nuclides again. By accelerating beams of particles and having them interact with matter, we're able to produce radionuclides well off the line of stability. This black line is called the line of stability. That's where the stable stable isotopes are. They're not radioactive. This is an example of all of the radionuclides that we would produce with different intensities if we bombarded a uranium target, which is up here, with 50 MeV electrons. It's essentially a fission process, slightly different than what happens in a reactor. So we can use the beam of the accelerated beam to discover new particles if we populate ones far enough from the line of stability, discover new nuclides. We study fundamental forces. We can also, by studying nuclides far from the line of stability, recreate processes that can only happen when you have sufficient amount of energy, like in a supernova. So a lot of the nuclear physics that gets done is actually called nuclear astrophysics because it has pertinence to those processes that go on in the when stars are born. We also manufacture radioisotope for medical purposes, and this is a picture of a PET scan. And then we've already talked about the commercial uses. Okay, getting on to regulating nuclear facilities. And I'm being mindful of the time. I see, yeah. So what I've got here is I've shown the 3 different classes of nuclear facilities. From left, the power reactors on the left, to the class 2 facilities, smaller research reactors, medical cyclotrons. TRIUMF is a class 1B facility because of the 520 MeV cyclotron. The energy makes it essentially more hazardous than a class 2 facility. And that's largely because of the dose that can be present, as we'll see, inside exclusion areas. And our regulatory program consists of 14 safety and control areas, and I will be telling you about these 3 of them in a little bit more detail. Oh, the radiation protection as well. It should have been in red. Yes, and we are, the CNSC conducts inspections 2 to 3 times a year, focusing on 1 or 2 of the different programs. They all get inspected in a 2 or 3 year rotation. All right, so what I need to mention is, or make a distinction, is between prompt radiation that we have when the accelerator is on. And here's our beam of 500 MeV protons, which you know is buried inside shielding. But when we hit the target, we make a lot of different exotic particles. The ones that are most penetrating, and some of these exotic particles decay as well. The ones that are most penetrating are neutrons and gamma rays. These are stopped relatively close to the target in the shielding. After we turn, and the dose rates associated with this radiation are in the thousands of sieverts per hour, as we'll see. Now, when we turn the accelerator off, we have residual radiation that remains. So we've made some of the components radioactive, as we saw on the chart of the nuclides. And of course, the long-lived ones, which are the ones that I've got listed here, are the ones that remain after we've allowed for a cool down period before people can access and do work. Note as well that we've got some airborne radionuclides that are formed as well in that process. So we have 3 different ways of protecting personnel from this prompt radiation. And as I said, it's a prompt radiation that makes us a Class 1B facility, makes us a more hazardous facility than some of our medical facilities. So we need to be able to shield for prompt radiation. And what I've shown here is the kinds of simulations that we do with Monte Carlo code, where we have our geometry here. Here's our beam coming in along the beam line, incident in this case, this is just a dump where we stop the beam, but it of course needs to be cooled. And then we have slabs of steel and concrete to really contain the radiation as much as possible. And you see that in this simulation here, that shows essentially the level of the dose rate in millisieverts per hour. And we, of course, would optimize the design of this to essentially get the best containment. But you see as well that we have a slab of concrete above this region because all of this is inside an exclusion area. And this is a slab of about 6 feet of concrete. So we get the dose rates down to millisieverts per hour inside the hall, and then outside where personnel can be, it's down at the microsievert per hour level. We also use a maze. This is a simulation now of a medical cyclotron, where this is the target here. And this is a region where we would like to access once the area has cooled down. And so we need to provide access into the area, and that's this maze here. And we use the simulations to essentially design the maze so that by the time you have personnel here at the gate, where people can be just at the gate, outside the gate, the dose rates are sufficiently low to allow that. The other mechanism for protecting personnel from prompt radiation hazard is our radiation monitoring system. And it is deployed both a component inside the shielding where the beam can be, and a component, the neutron monitoring system, outside of the shielding. And the component inside ensures essentially that we minimize losses in regions where we are thinly shielded, and ensure as well that where we do have losses that can't be avoided, the losses are not too high. And if there is a loss that's too high, the trip system comes in, both for these detectors and the neutron monitors outside shielding. And that would stop the beam. Okay, I wanted to talk about risks, occupational risks, and put the radiological risk in context for people. So I had this poll question here.
While this poll's running in, I'll just ask you how much more time you think you need.
I should be done in a little bit more than 5.
Okay, great, thank you.
Okay. Again, this is one that can have more than one answer, so.
All right, in the interest of time, I will end it there and share the results.
Okay, and the answers, in fact, both mining and construction have higher occupational risks And manufacturing is in fact comparable, as we'll see. Okay, and do I just close that then? All right. And I need to click here. All right, so personnel dose limits. The dose limits are set by the Canadian Nuclear Safety Commission, and they're based on studies of population exposure data. This actually could be a topic for a whole separate talk in itself. The limits are set to ensure that the risk is comparable to other safe industries, and you'll see that in a minute. That's why I say comparable to manufacturing, for instance. The nuclear energy worker annual limit is 20 millisieverts. How does that compare with other risks? So here's a 20 millisievert, so at the limit, and how that risk compares. So you can see that it's say comparable to construction, maybe a little bit higher than construction. But the reality is that most nuclear energy workers in Canada, and certainly that's the case at TRIUMF, their annual dose is closer to a few millisieverts, and that really then puts the industry in, comparable risks to, say, manufacturing. And as well on this slide, on this chart here, I've captured what the regulatory limit is for dose exposure to a member of the public, and that'll come in as we talk about environmental, and how that compares with other risks associated with everyday life. Here's our dose histogram for TRIUMF for 2019. Now, most of the radiation exposure comes from residual radiation. So when workers have to go in and do maintenance on components that have been made radioactive when the beam was on. And I've listed here some of the mitigation measures that we use in terms of training, job and task planning, and of course, dose monitoring. And this here shows our dose over the years. Now, what's interesting here that's not shown or not captured is that we, in the early years, had very much lower beam powers. We ran very much lower beam currents than we do currently. Now we've increased to about 3 times the beam power. So it's really interesting to see how, in order for us to be able to do that, we really had to work at, and these are the measures that we used here for reducing our personnel dose. And you can see we've been quite successful at doing that. Now, it's not only radiological dose that poses a risk to workers. And so I've captured here, just for information, how TRIUMF's injury rate compares with our classification unit from WorkSafe BC. I won't say much more about it. I will point out here that when we are looking at a serious injury rate, certainly TRIUMF's serious injury rate is significantly lower than some of the other sectors that we're compared to. All right, so that's personnel dose. Operating a nuclear facility also poses a risk to the environment and to the surrounding population. And that comes largely because radioactivity in the air of the cyclotron vaults and the beamline tunnels and other irradiation facilities is prevented from migrating to other parts of the lab by sealing those spaces and providing a negative pressure. So we provide that negative pressure to ensure that if there is any leakage, then the leakage is in. And we provide that negative pressure by a nuclear exhaust system, a nuclear ventilation system, and it's got redundancy with the standby fan. And what we have is we have monitoring of course, there's filtration in place to limit what is emitted, and then we monitor continuously with a radioactivity monitor. So here are some photos. You can see our shielded, lead shielded radioactivity monitors here. Here's some charcoal filtration on the hot cell exhaust. So that continuous monitoring means that we know, we do measure what we are emitting up the stack at TRIUMF. Now, in order to know what the impact is on the surrounding environment, we use a model, a pathways model that says, okay, for a given amount of radioactivity emitted in the source, how is that dispersed in the atmosphere? And we have our meteorological data that we use to model that. And some of it can just essentially is pushed downwind, and a member of the critical group could be exposed just from that air wafting by overhead. We also break it up into all of the possible other pathways that that radioactivity could make its way to a member of the critical group. The critical group is the group that has the potential to be most impacted. And we're using a standard formalism for this. It's in CSA and 288.1 standard. I'll add that to my slide when I send them to you. So what does that look like? If we take now our source and through the model and look at what is the dose impact to a member of our critical group. And here what I've shown is the dose, the regulatory dose limit, first of all, which is in red, and that's the 50 microsieverts annually for operation of a nuclear facility, a factor of 20 down from the member of the public dose limit. And this is TRIUMF's modeled dose to a member of the public. So we're at about the 20% level of the limit from that modeling. Well, in 2014, we thought, okay, well, we should actually endeavor to put a detector in place and see, in fact, what do we measure? And what you see here is a detector on top of the roof of a nearby building, about 350 meters away. And the measurement of the dose is shown here in purple. And that is about a factor of 2 to 3 times less than what our model predicts. So it's telling us that our model is in fact quite conservative. Now, this is the maximally impacted member of the public. So as we get further downstream, the dose is significantly less than that. But to put that in context, that's 4 microsieverts. That's at about 1/10 of the regulatory limit. And put it in context with natural background radiation that one is exposed to, which is about 300 times that level. So lastly, I just wanted to say a few words about decommissioning nuclear facilities, and I apologize for the very busy slide. It is a requirement of a nuclear facility to have a preliminary decommissioning plan. It became a requirement in the year 2000. TRIUMF put its plan together. It was a multi-year project. We did extensive sampling at the lab to assess the inventory of radioactivity in the shielding and the structures. The plan that we ended up putting in place takes a phased approach that reflects essentially the half-lives of the long-lived radioactivity in the building materials. And so we have 3 phases at time 0. It takes 2-3 years to complete the time 0 decommissioning phase. And then at 25 years, another 1 to 2 years to complete that. And then 50 years, by the end at 50 years, it's really the main 500 MeV cyclotron that is left behind after 25 years and gets decommissioned at 50 years. I've captured here some of the radionuclides that essentially drive this. And in this chart, you can see the unconditional clearance level set for these radionuclides. This is set by the Canadian Nuclear Safety Commission, and it's set based on looking at what's the potential exposure to members of the public if you release this material with no conditions attached. And the dose to a member of the public is again at the 5 to 10 microsievert per year level. So you can see that, in fact, for some of our higher dose materials, we are still above that unconditional clearance level. So some of the material will have to go to radioactive disposal site. And these are some of the considerations that go into the design of a facility to, in fact, limit the activation of the concrete. So this is a floor plan of our new IAMI cyclotron. And by adding some boron carbide, in fact, to the concrete, you're able to reduce the activity concentration from operation by a factor of 10. So we have done that. Of course, there are costs in doing that, but ultimately it helps in decommissioning. So in conclusion, we've seen that occupational and environmental health figure prominently in the design and operation of nuclear facilities. Our personnel dose, a TRIUMF annual dose of 2 to 3 millisievert is well below regulatory limit and poses a risk that's comparable to that from other industries. Emissions are monitored continuously and have an environmental impact to a member of the critical group that's at about 10% of the regulatory limit and corresponds to less than 1% of the dose that everyone receives from natural background. And lastly, a cradle to grave approach is a requirement for building a nuclear facility. And one has to have a decommissioning plan in place to do that. Thank you.